Okay, let's go ahead. Why explicit PRNG exists in Jax? This markdown cell explains difference between NumPy implicit global random state and Jax explicit key based randomness. In Jax, keys make random generation pure and reproducible, which works better with JIT compilation and functional programming. And this cell proves reproducibility. Two queries created with the same seed produce the same random values. Then we create a different seed and get different values. We can see these two have produced the same values and the third one has produced a different value. This is exactly why Jack's randomness is reliable and debuggable. Transition to data types. Next, we cover data types like int32, float32, float16 because D types affects performance and memory, especially in deep learning. This cell creates arrays using common Jax D types, integer, floats, and booleans. You might also warning. We might also actually see a warning um, about int64 and int64 and float64. That's because on many setups like here, like Jax runs with 64-bit disabled by default, and it will fall back to 32-bit. For deep learning, float 32 and sometimes float 16 are usually the main focus. So once we have print all these values, we can see the output here for all the D types. Next is type conversion. So here I would like to demonstrate like how the type conversion happens using dot as type. We can see dot as type. So we start. Let me start with float values. Convert into int32. Float values convert into int32, which truncates decimals and also convert to float 16. This is common when you want to reduce memory or match model requirements. So here we see how it got truncated. And next is transition to array properties. Now we look at array attributes, things like shape, dimensions, total size, d types, and device placements. So if you have to understand like array metadata, um, we can see like let's go to this cell. Here like this cell prints key array attributes, shape, shows dimension size, ndim shows number of ndim shows number of axes, sorry, ndim shows number of dimensions, array dot shape shows shapes, array dot size, array dot d type shows d type, and array dot device as shows the devices. These indicates whether the data is on CPU, GPU, or TPU. This is essential for debugging deep learning pipelines. So we can see like the CPU device is 0, and we can see all the respective values that we are trying to print. Next is transition. Next is transition, um, which is like indexing and slicing. These are the basic skills we should use constantly for batching, selecting features, or manipulating inputs. And next go to here we are trying to access single elements like it's like basic indexing. This cell demonstrates like basic indexing in 2D arrays. We access the first element using array 0 comma 0, and a middle element using 1 comma 2, and the last element using -1 like. And the indexing style feels like a numpy. So this is the array, and we see the first element is 1, the middle element is 7, and the last element is 12. So that's the output. Next is slicing patterns. Now we slice array using start, stop, and step pattern. We select the first row, first column, and a submatrix. Also very second row using step slicing. This is how efficiently we can extract batches or regions from tensors. Next is Boolean indexing. We create a mask where elements greater than 6 are marked true, and then we use that mask to extract only those values. Here we can see how we can extract. Masking is very common for filtering, thresholding, or selecting valid entries. We can see all the values which are greater than true or marked as true in this matrix. And then Jax arrays are immutable. This is a major difference. Jax arrays are immutable, meaning you can't update them in place like NumPy. This supports functional programming and makes Jax transformation safer and more predictable. And functional update is that here how to modify an array in Jax. Instead of in place assignment, we use at index here dot set value, which returns a new array. The original remains unchanged and the modified version reflects the update. We can see that like at the rate 0 as in fetch the like kind of set the value which is at index 0 to 100, and we can see that the new matrix has 0 index value as 100, so the original is same, it is unchanged. Next is set add multiply updates. This shells also shows more at operations. Here we can see setting a slice and adding to an element and multiplying an element. These are functions update patterns will majorly observe and also are used in many Jax programs. So as similarly set array sets like the first element in the 0 index element to like 0, and set 1 is to 3 as in the element at 1 to 0, and then add second element with a value of 10. The second element was 0 1 2, so this was the second element. Add 10 as in 10 plus 3, that's 13. Multiply second element with 2, that is 3 cross 2 is like 6. Next is transition to operations. Now we begin co-tensor operations, element-wise math, broadcasting, reductions, reshaping, and concatenation. These are the building blocks for neural network. First is element-wise operations. This cell demonstrates element-wise arithmetic, addition, subtraction, multiplication, division. Every operation happens position by position across the arrays, which is exactly how a lot of neural network math works internally. We can see for the arrays given here for A and B, after these arithmetic operations, these are the outputs like 5 plus 1 for addition and then 5 minus 1 for subtraction. So the arithmetic operations happen for A and B arrays. Next, common mathematical functions. Here we use the standard mathematical functions from JNP like sine, cos, exponential, log, and square root. These functions are vectorized, meaning they work efficiently across entire arrays. Very helpful for activations and transformations. We can see all the outputs for all these values. Next is broadcasting. These broadcasting letters operate on arrays of different shapes by automatically expanding dimensions when possible. It's super powerful, but it's also a common source of shape mistakes. So we will see clear example next. Broadcasting rules, and this cell actually demonstrates the broadcasting rules and demonstrates scalar broadcasting. Adding a scalar to a vector works because the scalar is broadcast to match the vector shape and the result keeps the vector shape. And this is the row broadcasting. Now we add a vector of shape 3 to a matrix of shape 2 cross 3. Broadcasting automatically applies the row across each matrix, producing a 2 cross 3 output. Sorry, this cell we can see. And we add a vector of shape 3 cross 2 3 comma to a matrix of shape 2 cross 3, and broadcasting automatically applies that row across matrix, producing an output of 2 cross 3. Next is column broadcasting. In this example, we add a column vector shaped 2 comma 1. This is the one, and to the same 2 cross 3 matrix. Broadcasting repeats the columns value across the columns, again producing shape 2 comma 3. Reshaping to 2 comma 1 is the key to making it broadcast correctly. And next is broadcasting to create a 2D results. This is really useful trick because multiplying a vector of shape 3 comma by a column vector of 2 comma 1 produces a new produces by a column vector of 2 comma 2 comma 3 result similar to an outer product. Broadcasting helps you to build a higher dimensional results without loops. Next, transition to reduction. Uh, Things like sum and mean, which are common in loss functions, pooling, and statistics. That's what we are going to discuss next. This cell performs global reduction across all the elements of a matrix. So this is a matrix. And next, we compute sum, mean, min, max, standard deviation, and product. These are basic but extremely common operations in training and evaluation. And in the output, all these values are printed for the matrix that we have given. Next is axis-wise reduction. Here we reduce along specific axis, axis 0, reduces rows and gives result per column, while axis is equal to 1, reduces columns and gives the result per row. Understanding axis behavior is a little crucial when while we are working with batches and future dimensions. And this is the output. See. Next is keep dimensions for broadcasting. This cell shows keep dimensions equal to true. Without it, a reduction removes a dimension, but with it, the reduction axis stays as size equal to 1. Keep dimensions is helpful when you want the result to broadcast correctly back against the original tensor. And then is reshaping operations. This cell starts with 1D array from 0 to 11, then reshapes it into a 3 by 4 matrix and also into a 3D shape 2 comma 2 comma 3. Reshape doesn't change the data value, only how they are viewed in dimension. So for example, this is the original. We have given reshaped into 3 cross 4. This will be arranged in 3 cross 4 format, and we'll ask for 2 comma 2 comma 3. It will get reshaped into a subarrays like this. Reshape with -1. So here we use -1 in reshape. -1 tells Jax automatically in for the correct dimensions size based on the total number of elements. This is very convenient when you know one dimension but want to the other to be computed. Next is flattening. This cell shows flattening on a 2D matrix into a 1D vector like using flatten and ravel. Flattening is very commonly used before feeding tensors into a fully connected layers. Next is transpose. Now we transpose a matrix, which is swapping rows and columns. Transport is fundamental in linear algebra, appears in many deep learning computations. As we can see, this was 2 cross 3, 2 rows, 3 columns. It has been transposed to 3 rows and 2 columns. Next is adding new axis. This cell uses expand dimensions to add dimensions. For example, converting a shape of 3 comma into 1 comma 3, as we can see here, or 3 comma 1. Adding access is often needed for broadcasting and for converting data into batch format. Next is squeeze. Here we do the opposite using squeeze. Removing dimensions of size 1, this helps clean up shapes after operations that introduce extra access. First is transition. Next we learn how to combine arrays using concatenation and stacking. This is common for merging batches or assembling features. So join along existing axis. This cell concatenates two matrices. Concatenation along axis 0 stacks them vertically, adding more rows. Concatenation along axis equal to 1 stacks them horizontally, and adding more columns. This operation joins along an existing axis. Here it's concatenated vertically for axis equal to 0. For axis equal to 1, it happens horizontally. Next is join along a new axis. Now we use stack, which is different from concatenate because it creates a new dimension. Stacking 2, 2, 2 arrays along axis 0 produces a 2, 2, 2 tensor, like grouping them into a batch. Next is convenient shortcuts. This cell shows convenient shortcuts like vstack. Is basically vertical stacking like concatenate on axis 0, and hit stack is horizontally stacking similar to concatenate on axis 1 for these shapes. So we can see. Next is why matrix multiplication matters. So I would say the most important operation is matrix multiplication because it's the heart of neural network layer. The typical forward pass looks like output equal input matrix multiplies by weights plus a bias. The key takeaway is shape compatibility and batch in futures, out futures, and then like which produces batch out features. That's the end of this Colab demo. In this walkthrough, we covered tensors, array creations, random keys in Jax, D types, indexing, immutability, broadcasting, reduction, reshaping, concatenation, and we previewed matrix multiplication for deep learning. And that's it for this demo. Thank you.